Please join me in welcoming to the Distinctive Voices podium, Dr. Bethany Ellman.
Okay, great. Welcome to our lecture this evening, to those in the room and those listening online. So I'm excited to talk to you about a project that we've been working on the past 5 years that really represents a new way for NASA to execute robotic planetary missions in the solar system. So this is going to be a roaring tour in 45 minutes because it's really a talk in 3 parts. Which is, the first part is the science of water on the moon. What does that even mean? The second is about small satellites as a mode of exploration. And then the third is about our project, the Lunar Trailblazer mission, which launches in just about 4 months from today. So let's talk about water. Water is key for life on Earth. But think for a moment, why does Earth have water at all? I mean, we have it, but why? Where does it come from? Well, so originally, water comes primarily from 3 sources. When the Earth was forming, water was a part of the initial materials that were accreting together in this picture I have here of a protoplanetary disk. Lots of small granules like this, which have water in them, small amounts. Then delivery by impactors, asteroids and comets, some of which were icy. And then finally, once all of that was in Earth, then Earth's mantle actually, so under the crust, Earth's mantle actually has water in it as well. So when volcanoes erupt, part of the gases that come out are water. So that sort of replenishes our water. Because meanwhile, what's going on all through time is that some of the water is being lost out of the top of the atmosphere into space by various processes. Okay, so that's why we have water. But I'm talking about the moon. Should the moon have water? Well, so when you look at the moon, maybe you think it's a beautiful orb in the sky. It is. You look at the dark basaltic mare or plains. They look like seas, but they're actually dark rocks, and then the light-toned highland rocks. Do you think about the moon's temperature? Yeah, it's out there in the vacuum of space. There's no atmosphere, and the moon is actually hot, mostly. Some places not. We'll talk about that. So this is a graphic where you can imagine that you are the white dot. What we're looking at here is the equator of the moon, and these are different longitudes. The time lapse is you're experiencing a lunar day, and this is a little bit of a typo. The day in terms of when it is daylight is 14 Earth days, and then it is night for another 14 Earth days. So it's a 28-day cycle where if you're standing there on the surface of the moon, you're actually experiencing, here comes sunrise. The temperature rises, goes up to like 400 degrees Kelvin before, so sunrise, very sharp temperature rise, 400 Kelvin, and then a sharp temperature drop to very cold temperatures. So it's a surface of extremes. That's because it rotates very slowly, so it actually heats up more, in fact, than our own Earth does. But then when the sun sets, there's no atmosphere to hang on to the heat, so it's just radiating out against the dark to dark cold space. So would we expect water to survive? No, I mean, not liquid water and not even ice. What would happen to ice is very similar, dry ice, like CO2 ice. It doesn't, it goes straight, in fact, from the solid phase to the vapor phase. This is what we would expect would happen to any liquid water, which is unlikely, but any solid water ice on the surface under these kinds of temperatures and against the vacuum of space would simply sublime. But if you were looking at this map closely, you may have noticed I put a second dot, another dot down at the poles. So in these measurements of temperature, you notice it's a bit, more heterogeneous down here. There's a lot more going on. This is not like some kind of noise in the data. This is actually real. Why is this? What is going on at the poles of the moon? Well, what's going on at the poles of the moon is that there are craters right at the poles where the sun, because the moon rotates straight up and down, the sun comes in at an angle. And if you're deep in these craters and that sun comes in at an angle, there are places that are in permanent shadow because the sun never shines there. It's just at the poles and the rotating straight up and down, the sun is coming in, and if you're in a depression, there are parts of that depression where the sun don't shine, ever. And so as a consequence, it is very, very cold in these depressions. Okay, we haven't gotten to water yet, exactly. So this is a story that has a Caltech beginning, actually, so I had to show this. This was before my department was the Division of Geological and Planetary Sciences. It was just geological in those days, May of 1961. Grad student Ken Watson, who I had the pleasure of meeting, actually, a few months ago, wrote with his advisors. He was actually arguing with some luminaries in geology and geochemistry, like Urey and Kuiper, which some of you who are science aficionados might know those names. But prior to this paper, there had been an argument that no solid or liquid water could exist on the moon. But they argued that water was actually far more stable on the lunar surface. And they accompanied these by some calculations. They said, actually, you folks who said there could not ever be water on the moon didn't think about something. That if there were ice that came into being from a comet, or if there were volcanic gases that ended up in those cold, cold traps, the water could stay there. Why? Well, it was a little bit of math. They said that, well, as temperature gets lower, this is a funny axis, it's inverse temperature, so temperature is actually getting lower as you go this direction. So as it gets colder, going this way, the rate of evaporation of water, here's water on this plot, the rate of evaporation of water drops dramatically as a function of temperature. Those of you in the front of the room who know log scales can see this drops by almost 20 orders of magnitude, 10 to the 20. So that's 10 with like 20 zeros after it. So it makes a big difference whether you're hot or you're cold in terms of how quickly that water is lost to space. If it's cold, yeah, it's going to sublime, but it does so very, very slowly. So one can do some calculations, and one can compare this to actually what are the temperatures that are measured at the pole of the moon. So now we're looking at the South Pole. We're down here. And we're looking at a map where these are the temperatures that have been actually measured by the Diviner spacecraft, which was led, the instrument on the Lunar Reconnaissance Orbiter, their Diviner instrument, led by my colleague Dave Page, who's a professor at UCLA. What that team measured is in these cold, permanently shadowed regions, it is very cold, 75 degrees Kelvin. You know, for example, like liquid water, the freezing temperature of water is up here. So we're very, very, very cold. And in fact, we're so cold that if you're about 110 Kelvin, that loss rate, the evaporation is so slow, you only lose 1 millimeter every billion years. That's slow, right? You could wait around a long time for that water ice cube to change, a whole lifetime, and you wouldn't notice anything. And so that said that if any water got stuck here, it could stick around for the entire lifetime of the solar system. Or, conversely, if there were water as gas, it could actually get trapped, cold trapped, into these regions where it would freeze out as ice. So then the question is there any ice in any of these cold traps on the moon? This has gotten people excited. People talk about mining water on the moon, a lunar economy, moon bases at the South Pole where we're going to get the water. But is there any water there? Well, we've investigated this. The royal we, the scientific we, has taken a look at this already. One of the things that was done is that NASA sent a mission called LCROSS that some of you might remember, because in, I believe it was late 2009, early 2010, there was this spacecraft that sent a projectile into one of these cold, shadowed regions of the moon and then watched the plume as that projectile came out. And the question was there any water in that dust cloud? And the answer was, well, yes, there was. This is a infrared spectrum. This absorption feature is due to water in the solid form, and the estimates are, not too much, like about 2 to 8 weight% in the plume of dust. There were some other gases, other volatiles in there as well, along with water. So that's interesting. We know, okay, at least in this place, there was some water on the moon. Then the question is, well, how widespread is it? And this is where we don't quite know. The map that you see here is a map not exactly of water, but it's a map of hydrogen. And it's specifically hydrogen in the upper half meter, so about 1.5 feet or so of the surface. It's measured by looking at the neutron flux from the surface. And so over a very large footprint, both the Lunar Prospector neutron detector and then the LEND neutron detector after it mapped the poles, mapped the whole moon really, and there were these patchy bits that did correspond to those dark, cold regions that showed elevated amounts of water, but not very much. 0.5% by weight. Now, the thing is, though, the footprint of this instrument was very large, larger than the footprint of this building. So if you're getting 0.5% by a weight, a key question is, well, is there a big block of ice? Is there a big block of ice here? And if you go over here, there's nothing? Or is there just a teeny tiny amount spread evenly over this whole patch that's, the size of the footprint of the city of Irvine? That kind of matters if you want to send a rover or an astronaut to go investigate it, whether you're looking at a few blocks of ice within a big area, or you're looking at the same amount spread evenly throughout the whole area. So this is a big question. A different instrument, in a very few of these cold traps, about 3.5% of them, found, those of you who in the front can maybe see this gray line, which this red line is then fit to the data, some evidence in reflected light spectra of water ice in the cold traps, but not very much and not in all of them. So where we sit as of right now, this moment, is we know there is sometimes water on the moon. There's a few other missions that have been sent looking for it. A NASA instrument ShadowCam on Korea's first lunar mission. Did you know that Korea has an orbiter around the moon right now? And it carries a NASA instrument called ShadowCam, which looks into these regions. But while there are some bright regions, they seem to mostly be related to the illumination angle. There's no screaming, smoking gun of water ice. So they're putting an upper limit of abundance on 20%. At the same time, my student and I are re-examining some old data sets, and we're seeing in the albedo data some patches where maybe there's suggestions of water ice, but these data don't allow confirming it at the moon. So we know there's some water ice in some places, but we don't know exactly where. This is the state of the science on the moon, and we don't know exactly how much. It seems to be a little bit elusive. Meanwhile, though, on Mercury, and I have to say, as a planetary scientist, I can just be on the moon, and then meanwhile on Mercury, this other airless body in our solar system, it's the closest planet to the sun. Like the moon, no atmosphere. It's a bit bigger than the moon, by not hugely so. Meanwhile, though, we did send a spacecraft to Mercury, and we also have probed the poles with radar signals from Earth. And actually, the poles of Mercury, it's the same situation, rotate straight up and down, has these craters. The permanently shadowed regions on Mercury are actually full of ice. They light up in all the data sets. They're bright in radar deposits. That's not the case in the lunar data. There's some neutron spectrometer data that indicates even higher concentrations of hydrogen. And there's even some carbon in there, which might indicate that comets or something crashed into the poles of Mercury. We don't know yet. That story is still being unraveled, but it's certain that there's ice in these regions on Mercury. Okay, so this is interesting, right? We've got a lunar mystery. There is ice, but not as much as we might think based on other planets. In the meantime, something else happened on the moon at right about the same time. The 2009 to 2011 was a kind of exciting time for water in the solar system. There was a mission that was sent to the moon as part of India. So India also has sent an orbiter to the moon, Chandrayaan-1. And there was a NASA contribution on board from JPL here in Southern California, the Moon Mineralogy Mapper instrument. This is what it looks like. It collected maps of spectra on the moon, and its name was the Moon Mineralogy Mapper, not the Moon Water Finder or anything like that. But it had a surprise in the data set. So the surprise was this 3 micrometer absorption, which if you map it across the globe, it got a lot deeper as you went to the poles, the cold poles. So this is kind of at the middle latitudes. And then as we went to the poles, the M-cubed team noticed that there was this absorption in the data set that just got stronger and stronger as you went to the poleward. What causes a 3 micrometer feature? Well, water or hydroxyl. So the data, all of these substances cause this, and very few others, cause this 3 micrometer dip. But M-cube's wavelengths cut off right here. These were not measured. Why? It was the Moon Mineralogy Mapper. They weren't expecting to go looking for water. But then there was this mystery. So what is this? What was this? The mystery deepened a little bit when people looked closer, because then they found, well, certain landforms and craters, certain volcanoes had this dip in it. In a different data set, this was a spacecraft called Deep Impact, which had flown by the moon many decades earlier, but the data were then re-examined after M-cubed started making these peculiar findings. They had some flyby data that they had taken the same part of the moon at morning, noon, afternoon, and evening, and in the hottest parts of the day, noon and afternoon, that 3 micrometer water absorption looked like it got a lot smaller than during the morning or evening. So is there some process analogous to like how you get dew in the morning on the surface? When it's cooler, you get that layer of dew. Is something like that happening on the moon with H2O coming and going in patches on the surface? So this was important. This was a key mystery. A confounding factor is that your thermal model matters in terms of figuring out how much water. So now we're going to get a little bit nerdy and talk about black body, as if we weren't already. But we're going to talk about black body radiation. So everything radiates as a function of its temperature, and that radiation gets stronger and moves to lower wavelengths with heat. So here's our water absorption that we care about. What you see is that as the surface heats up, it starts to interfere with our water absorption of interest. So by the time it's kind of fine at night, morning, noon, but the question of whether water varies as a function of time of day, you have to know the temperature very well, because you have to know how to correct for this black body radiation effect. So where our state of the science is, we don't know how much water there is right now. And the other question is, what is the form of this water? Is it coming and going? Is the right way to think about, the water everywhere as actually like ice? Like you'd recognize it as like a snow or an ice cube. Is that the right way to think about it? Or is the right way to think about it like the thinnest of like a dew on the lunar surface, where you have water molecules hopping around, forming layers on the soil when it's cool? Or is it actually trapped in minerals? It's not exactly water at all, it's hydroxyl. And there is a solar wind of protons that comes in, so that's not implausible. But what's kind of fun as a scientist is that these types of questions that I'm asking, like they're pretty new questions. We weren't asking them until about 2010 or so. So people learn about, the water cycle on Earth, in 3rd grade or something, right? We have our rain, water flowing into the sea, back into the atmosphere, and this is our water cycle. We're at the start of a new set of questions about the water cycle on the moon, on Mercury, on other airless bodies. We know that these had volcanic activity. So did the water go form a temporary atmosphere and then condense back to the surface and make its way into these dark craters?
Or was it a rain-in from comets and asteroids and micrometeorites? Again, that water then making its way preferentially to the colder regions, getting trapped there. Or is the protons that are coming from the sun, are they embedding themselves in the soil and sort of confusing our data set? And then how much of this is lost to space over time, just as water is lost on Earth? So these are some of the questions right now at the moon about water. Now, that brings us to part 2 of the talk, which is small satellites and how we explore. Some of you may have seen this picture before because this was taken by one of the pair of twin satellites called Marco, which they launched with the InSight mission that JPL sent to Mars in 2018. And this is a picture of a satellite solar panel and Mars from the Marco satellite. How big are these small satellites? Anyone know? That's one of them. So this cereal box-sized craft, 2 of them, in fact, launched off of Earth with InSight, and they made their way under their own power to Mars, where the reason they were launched in the first place was to relay the data from the InSight landing back to Earth. It was kind of a helpful relay of that data to know that InSight landed successfully. But it also really kind of triggered a bit of a revolution because we realized that, hey, do we always have to send big missions to go exploring? If we can send a cereal box-sized satellite with a camera to take a picture at Mars, what other science can we do at small packages, at low cost? Something, a small team can assemble and do. So SmallSats have really been a revolution. They actually started in 1999 at Stanford and Cal State San Luis Obispo, where a couple of engineering professors got together and said, hey, wouldn't it be great for our classes to learn how to make spacecraft, like our engineering students to actually make and launch spacecraft? And what they realized is that every time when a launch vehicle launches, a company buys a rocket that is typically bigger than what they need for their spacecraft. It's economics, right? You have to buy the rocket ahead of time, and you don't yet quite know exactly how big your spacecraft is going to be. But you don't want it in the end to end up with a spacecraft that's too big for the rocket, so you buy the bigger rocket. But then at the end, you typically end up with some extra mass. You don't need it all for your spacecraft. And what these faculty realized is that, well, if you designed something that, the primary payload that was launching with the rocket didn't care what was inside the box, then you could put anything, really, inside the box and take advantage of the fact that there was all this extra mass available to bring things up to orbit. So, there's really been a revolution, and when you hear about, the SpaceX Starlink satellites, the OneWeb constellation for internet, Planet Labs and its monitoring of Earth, there are numerous companies that are using these CubeSat or SmallSat factors. And one thing that's happened now, just in the last 5 or 10 years, is now small is not always so small, because sometimes the amount of mass that's left over is hundreds of kilograms, if not tons. And so another way of getting to space are on these ESPA rings, expandable payload adapters. And this is an example of how it works. This is a rocket fairing. You can kind of see the outline of like the tippy top of the rocket where it's enclosed when it launches. The big spacecraft is at the top of the stack, but they put these rings in, and then this spacecraft, and this spacecraft are also hitching a ride at exactly the same time. And they can do that because even though they're incredibly different from one another, they can do that because they're of this standardized interface. So as long as you can bolt your spacecraft into that interface and you tell them what mass you need, good to go. So it's a whole new mechanism that's lowering the cost to get to orbit and making possible these CubeSat and SmallSat missions. It's really a new way to explore, a new way to observe Earth, new way for telecom. And so that brings us to part 3, where parts 1 and 2 get melded together into the Lunar Trailblazer mission. So the origin of our mission is in a question that had some constraints around it, like a box around it, which is what big science can you do with a small spacecraft? And NASA's hypothesis was that for select science questions and at a higher risk posture, meaning lower cost, higher risk, I'll talk a little bit about that, it is possible to actually do some really important planetary science out beyond Earth with these small spacecraft. So the call was called Simplex because everything's an acronym. So this was the Small Innovative Missions for Planetary Exploration. And Simplex were these ride-along missions that took advantage of the extra mass. They had a tight cost cap. You traveled on one of those rings. The goal was to bolt into one of those rings. Class D implementation, which means higher risk, but seeking top-level National Academy of Science, Engineering, and Medicine prioritized once every 10-year decadal survey objectives. I'll say in Lunar Trailblazers, there's also a very special role for Caltech and KISS. When I started as a young professor, I mostly had studied Mars, but a couple of colleagues of mine, Dave Page at UCLA, Paul Hain at JPL, my professor colleague at Caltech, Andy Ingersoll, invited me to be part of this group at the Keck Institute for Space Studies that wanted to seek new approaches for answering this water question on the moon. So all the way back in 2013, we said, hey, we should send a small satellite, like a Lunar Trailblazer, to go and do this. And then there's also a special role sometimes for the proposals you don't win, because a big reason that Lunar Trailblazer exists is because I worked with some colleagues just a year before to propose a mission for water mapping on that Korean lunar mission. We weren't picked, but we got a lot of the science discussion done that prepared us to propose Lunar Trailblazer and then be selected as a small satellite with the goal to understand the form, abundance, and distribution of water on the moon and the lunar water cycle. Our spacecraft would get hooked onto one of these ESPA rings, carrying 2 instruments, an imaging spectrometer for measuring water, and a thermal mapper for measuring temperature and composition. We go into a lunar orbit about 100 kilometers polar around the moon. I lead the mission with management and project systems engineering at JPL. Our flight system's built at Lockheed Martin, Denver, which is where I started the day. Actually, we just had the pre-ship review for our spacecraft prior to shipping it to Cape Canaveral, so that was exciting. And our mission operations is at Caltech in the IPAC Space Telescope group there, along with students, student undergrads from both Caltech and Pasadena City College, who are working as integral members of our operations team. So I don't need to, I think, belabor this. I'll just say we want to determine what is that water? Is it ice, H2O, OH? How much? Where is it? And how does it vary by latitude, the age of the soil, the type of rock? Does it change with time? So these are things we're asking about the sunlit moon. And then in the shadows, we want to peer in these shadows and figure out, let's map the ice. Where is the ice? Is it even there? Is it at the surface? Let's make the maps that answer those questions of how water varies with temperature. And in the meantime, we're going to get some of the best maps of what rocks and soils are made of to help pave the way for future landed missions and for astronauts who want to go to these sites. But what does it mean to be a Class D low-cost mission? This is Lunar Trailblazer and its cost, which is still a lot of money, right? But in a relative sense to some of the other missions that you might be familiar with from the news, our circle is a lot smaller than the Europa Clipper, for example, which launches just in 2 weeks from Cape Canaveral. And Grail was the most recent other mission to the moon, so we're about a factor of 5 or so 4 or 5 less than Grail as well. So how do you do a space mission for a comparatively smaller amount of money? Well, you have to be really focused on what it is that's new and what it is that's important about what you're doing, and I'll talk about that a little bit in terms of making focused science choices. And then you have to make compromises, or you could frame it as seizing opportunities to deal with some of the challenges of being a small sat and having a small amount of money. Strong university roles, allowing some risk to save cost. We couldn't afford NASA paying for more than one instrument, so we teamed up with the United Kingdom Space Agency and some collaborators at Oxford who agreed to contribute. They would fund the build and contribute it to hitch a ride to the moon on our mission to get temperature at the same time. We took a targeted approach to data acquisition because we could not afford a big comm system. You'll see that we do not take a direct route to the moon because we cannot afford a large propulsion system. And then really, though, the team is very important. Keeping the team small, skilled, but involving students is actually a win-win all the way around because students are getting training opportunities. And frankly, students don't cost as much. You know, just starting out, right? Rather than the software engineer who had 20 years of industry experience. We have a couple of those, but then they mentor like 4 students, right? And so there's really a win-win here in terms of training the next generation and getting folks involved in missions. Just a little bit about our data. Don't worry too much about the text. So we're from our orbit, we're making strips along the moon, but we can only actually take data in little kind of postage stamps. So we have a target bank on the moon of these different locations where we're acquiring our data, and we collect these image cubes where both of our instruments collect data at exactly the same place and exactly the same time. So one push brooms across, and for every single pixel in the image, HVM cubed has a spectrum that lets you get here at the spectrum of, oh, you can't see my cursor, at the spectrum of water ice here for every single pixel. At the same time, nested within are the images from the lunar thermal mapper that give temperature and the composition of the surface at exactly those same points. So it resolves that ambiguity between the amount of water, what the surface is made of, and what the temperature is. Our most sensitive measurement by far, and the driving requirement in the spacecraft and the design, is our HVM cubed, our high-resolution volatiles and minerals moon mapper, which has heritage from M-cubed, the moon mineralogy mapper. HVM cubed has a 1 part per 100,000 level measurement, and that's because in permanently shadowed regions, we want to be able to distinguish the absorption of water versus OH at a level that we're confident in the answer. So at this point, the savvy of you might be like, but wait a minute, aren't you using sunlight? Didn't you say visible shortwave infrared? That's reflected sunlight. You're looking in shadows. How do you do that? So here's what we do. It's actually an indirect measurement. So we are peering in shadows. There is no direct sunlight. So what we're actually doing is looking at terrain scattered illumination. So in those permanently shadowed regions, the sun doesn't shine. However, the sun does shine on the rims of these craters, some of which reflects light into those permanently shadowed regions, and then back outward to our spacecraft for measurement. So that's how it works, and that's why we have to be so sensitive, because it's a low light level. It would probably be equivalent to the light level here if we, it's not like pitch black dark. It's more like if we were to turn off all the overhead lights here, and then there was just the light from the glow in the back of the booth illuminating this auditorium. That's kind of the analogy. I won't ask us to demonstrate now. Maybe after. The mapping, as I said, is sweeping across in these polar orbits across the lunar surface and then taking targets as we go. So we have 2,000 some targets in our target deck. Our imaging spectrometer takes light, sends it through a telescope HVM cubed then sends it through the spectrometer where it separates the light out into different wavelengths and then onto our detector, building up the image. And it really takes advantage of a lot of JPL's best technology, matured over the years and miniaturized over the years to allow it to be used on these small satellites and also small landed missions. And I have to say, kudos to the entire HVM Cube team at JPL, and it is really gratifying as a scientist where the instrument that you imagine with the engineers at the beginning of the proposal several years later actually looks like your PowerPoint presentation. It's pretty amazing. And it's a beautiful instrument. It meets all of the requirements to do that 1 part per 100,000 measurement. Our transatlantic partnership with the University of Oxford and that student-led group in atmospheric physics. Here you can see some of them hard at work. I'm very pleased to say it builds on the UK Space Agency's miniaturization efforts. They flew an Earth CubeSat that was a technology demonstration that proved out some of the technologies. And again, the actual hardware that's going to go into space matches the diagram. So light comes in, it passes through a filter assembly at an intermediate focus, then back onto the detector. And the optics of this were built by Rory Evans, who's a PhD student at University of Oxford, and then he gets to take an infrared photo of himself with his PhD project that's going to fly to space, which is pretty cool. So this is our spacecraft. It's about 200 kilograms in mass and about 3.5 meters solar panel to solar panel. This is me next to a plywood mock-up that the Lockheed Martin interns put together to test the lengths of all the harnesses and cabling prior to cutting them to the lengths to go in the spacecraft. So making plywood boxes to model your harnesses is another of those cost-saving measures. But that gives you a sense of what the scale of the overall spacecraft is. There's a lot of work in design. The first 2.5 years were design and the acquisition of the various components, and then it all comes together, fairly quickly. In August, it was panels with that harness that I talked about. That lengths had been measured in the cardboard box. So the panels were then assembled. The harness that was going to connect all the components on the inside, all the cabling was strung. The propulsion system and the fuel tank came in. Note the size of the fuel tank with people. Most of this spacecraft is the fuel tank, okay, to get to the moon. Here's HVM cubed, our water sensing instrument being installed on the top. The entire spacecraft in TVAC. This is a beauty picture with HVM cubed as well as uncovered lunar thermal mapper, our UK instrument. And then the spacecraft folded with spacecraft solar panels folded up on the spin table. This gives you a little sense of what the solar panel length looks like during the deploy, and this is us on the vibration table because you shake the spacecraft and you try to break it prior to sending it to orbit, and then you fix things that go wrong. So we concluded that process earlier this year, and then I was very pleased that the very final tests, like solar array deployment, we ship with them buttoned up and then have to deploy as soon as we're released from the rocket. And so just a few months ago, we proved out that this is the final test. And we are now, as of yesterday, or earlier today, really, through the final actions coming out of our pre-ship review, and we'll be going to Cape Canaveral just before Thanksgiving. The route to get to the moon is a little interesting. How long did it take the Apollo astronauts to get to the moon? Like a handful of days, 3 days or so, right? Yeah, it takes Lunar Trailblazer on the order of months, and it's very sensitive to which day we launch. Why is this? Well, we actually go and then we slingshot past the moon and we work our way back. Why in the world do we do this? Well, it's kind of the difference between your propulsion system being like, I don't know, the Volkswagen Beetle versus the Ferrari. So the Apollo astronauts had the Ferrari. Remember that an object in motion stays in motion unless it's acted upon by an outside force. So when you launch a rocket toward the moon, you are going toward the moon. And if you want to go in orbit around the moon rather than crash into the moon, you have to slow down. And you have to slow down quick. But guess what? Lunar Trailblazer the rocket is not as big and not as powerful as the big rocket that launches up on Earth toward the moon. So part of the reason for the circuitous trajectory is to shed enough of that energy, basically, to allow us to insert into lunar orbit rather than just smacking in the moon after a few days. We have to insert into lunar orbit. If we had a bigger engine, we could do this faster, but we have what we have. And so our mission phases is that we launch, this should be December 24/January 25. The launch window is right at the end of this calendar year. We launch with sharing our ride to the moon with Intuitive Machines lander number 2. Remember Intuitive Machines, first commercial US company to land on the moon? They landed, and then there was a little tip, but they landed. So this is going to be their second lander, and we're hitching a ride on the same rocket. After some trajectory correction maneuvers, we enter into our trajectory, followed by a reduction phase to pull the orbit down, and then it'll probably be about a 16-month science phase in orbit around the moon. I mentioned that our operations center is at Caltech. This is a new capability for Caltech. Caltech for a long time has operated space telescopes. This will be the first full end-to-end mission that we're commanding in deep space out of Caltech's IPAC. We actually sit in the same room that was used by the Spitzer Space Telescope, working with some of the same staff. But one of the key elements is that we're including, as part of the staff, students from PCC and Caltech. And so in our operations readiness tests, or ORTS, everything's an acronym. So operations readiness tests, we practiced launch and getting to the moon, and 91% of the time the console position that was communicating with the spacecraft, the ACE, was staffed by the students. So those students get to staff missions on console. They design pieces of our software for looking at telemetry. They're designing and proofing operational procedures, designing our scheduling software, and making many of the graphics that you have seen in this presentation. So we have artists as well as scientists and engineers working as part of the mission. Something that I just think is cool. Some of you, anyone seen this graphic before? The NASA eyes on the sky. It shows, you can go online, and if you Google the Deep Space Network, you can see where all NASA's dishes around the world and what spacecraft they're communicating with. There's 3 dish stations in Madrid, Goldstone, and Canberra. This is a really cool website to just go check out occasionally and see who we're talking to, whether it's the Voyager mission or the Psyche mission, or this was a test, that Lunar Trailblazer, LTB. We're not up in space yet, but we were simulating the comlink, so got a nice screen cap there. I think I'll skip this because I already talked about it. So what lies ahead for us? We were proposed in 2018, selected in 2019, and it's not like anything happened in 2020, 21. So it's been a hard road to get this spacecraft developed, but we are now at the end. We are flight system complete, and we're just about to launch at the end of this year with Intuitive Machines. So here's our stack and our ESPA rings. This is the Intuitive Machines lander. Here's the ESPA ring, and we're nestled next to some other spacecraft hitching a ride to the moon. So it's exciting. We're answering questions for science and exploration about lunar water, pioneering and prospecting where the future landing sites might be at the South Pole of the moon. We're doing it with a SmallSat among the first time in planetary science involving students, and it's the start of an exciting journey. So thank you for listening, and happy to take any questions.